This is part 3 of the video notes for Objective 7, Solving Equations with Inverse Trig. In this part of the notes, we're going to take a look at a variety of alternate equations that we can solve using inverse trigonometric functions. For our first example, we're going to keep it pretty simple and take a look at a problem where the angle is a double angle. So when you're looking at a trig function like this, it's important to note that the 2 alpha is in the input of the function. So when we're doing our operations to each side of the equation, we can't actually do anything with this 2. We can't divide both sides by 2 since it's a part of the input. What we can do is use an inverse function. I know that the 2 theta, so the input will become the output, equals the inverse sine of 1. Where on the unit circle does sine equal 1? Sine is equal to 1 at pi halves. And then how often does this value repeat? Notice I still have it as equal to 2 theta. So my last step is to divide both sides by 2. Let's try another problem that's slightly more complicated than this one. Example, we're going to increase the difficulty by adding additional operations in order to solve the equation. So take a look at this. Notice that there's an operation in the input as well as operations outside of the trig function. We're going to begin by using inverse operations on the outer portions. So we'll add 1 to both sides. We'll divide both sides by radical 2, and at the same time, we'll go ahead and rationalize our denominator. And since for the last example, we found all real solutions, let's restrict these to only solutions on the unit circle, from 0 to 2 pi. So let's think about all of the places around the unit circle where sine of an angle is equal to negative rad 2 over 2. That's true both in quadrant 3 and quadrant 4. So our two solutions are x plus pi fourths is equal to 5 pi fourths for quadrant 3, and x plus pi fourths is equal to 7 pi fourths for quadrant 4. Subtract pi fourths to both sides of the equation, and we get x is equal to 4 pi fourths, or pi, and x is equal to 6 pi fourths, or simplifying 6 pi fourths, we get 3 pi over 2. Let's take a look at another example. For this example, we're going to go ahead and solve an equation involving a reciprocal identity and see how we can apply skills we've learned in the past to new types of problems. So we're going to solve cosecant of 2x is equal to 2 rad 3 over 3 for the interval 0 to 2 pi exclusive. Cosecant is the reciprocal function of sine. So we're going to reciprocate this equation. Sine of 2x is equal to 3 over 2 rad 3. Go ahead and rationalize that radical. Sine of 2x is equal to 3 radical 3 over 6, or rad 3 over 2. And then because we're restricting ourselves from 0 to 2 pi exclusive, we're just going to be looking for angles on the unit circle where the sine value is rad 3 over 2. So that happens once in quadrant 1 at pi thirds, and once in quadrant 2 at 2 pi thirds. Dividing both sides of the equation by 2, we get our first answer is that x equals pi 6. And for our second answer, we get x equals pi thirds. All right, let's take a look at another example and see if there's anything we can change about this equation to increase the difficulty. For this next one, we're going to take a look at equations that are quadratic in format rather than linear in format. And remember that a quadratic function is one where the input value is squared. So our first example involving a square will be to solve sine squared x for 1/4 over the interval 0 to 2 pi. Well, the inverse operation of square is square root. So we'd begin this problem by taking the square root of both sides. What's the square root of 1/4? The square root of 1/4 is plus or minus 1/2. Remember, when we introduce a square root, we open up the opportunity to have a positive or negative value, since both square to be positive. That leaves me with a lot of options. I need to find all of the angles on the unit circle whose sine is 1/2, and all of the angles on the unit circle whose sine is negative 1/2. So let's start in quadrants 1 and 2. Sine is 1/2 at pi 6. Sine is 1/2 at 5 pi 6. Sine is negative 1/2 at 7 pi 6. And sine is negative 1/2 at 11 pi 6. How would we write this answer if instead of asking ourselves for the interval 0 to 2 pi, we instead wanted the interval of all answers? Well, some of these have a relationship. For example, pi 6 and 7 pi 6 are pi away. So we can write these two answers. If instead we were trying to find all solutions, we can write these answers as pi 6 plus pi k. And the same relationship exists for 5 pi 6 and 11 pi 6. They're pi away from each other. And so we can write this relationship as 5 pi 6 plus pi k. So if instead of asking ourselves for the solution on the interval from 0 to 2 pi, instead we wanted the interval of all real numbers, we could write our answer as the set of all x's where x is equal to pi 6 plus pi k, or x is equal to 5 pi 6 plus pi k. So when you introduce the idea of having a square as a possible operation, you're also introducing the idea of being able to factor or use the quadratic formula in order to solve problems, because those are quadratic strategies for solving quadratic equations. Let's take a look at one example of using factoring and one example of using the quadratic formula in order to solve an equation. So for our factoring example, let's take a look at the equation 2 sine squared x minus sine x minus 1 equals 0 from the interval 0 to 2 pi. Now you can leave the equation like this and factor it just the way it's written, or you can use a process of substitution, which is a common strategy in calculus, where rather than leaving sine x in the problem, I can substitute sine x for a simpler expression. So let's say u is equal to sine x. That means this equation is 2u squared minus u minus 1. This expression may be simpler to factor than this expression, and that's where U substitution is generally used. Well, now we need to factor this trinomial. I know that the only way to get, or one way to get 2u squared is to have 2u times u. And there's only one way to get -1, 1 times -1. The question is, should the 1 be here and the -1 be here? Or should the 1 be here and the -1 be here? I'm going to test my solutions. Let's go ahead and put positive and negative. If these are my factors, I would get 2u squared minus 2u plus 1u minus 1. Is this expression equivalent to our expression? Since -2u plus 1u is -u, these are the appropriate factors. Now, once we've factored a quadratic, this strategy works because of the zero product property. If I have the product of two terms equal to 0, that means either the first term is equal to 0 or the second term is equal to 0. So I'll solve both. That means that u is equal to -1/2 or u is equal to +1. Well, don't leave your answers like this because we substituted to get u in our equation. If you remember from the beginning, u is equal to sine x. Sine x equals -1/2. Sine x equals 1. Since we've restricted our solutions to be on the unit circle, we just need to think of the angles on the unit circle whose sine value is -1/2 or whose sine value is 1. This leaves me with a final solution of quadrant 3, we have 5π6. Quadrant 4, we have, quadrant 3 is 7π6. Quadrant 4 is 11π6. Then over here, we have sine is equal to 1 only at pi-halves. So the solution to this equation is 7π6, 11π6, and pi-halves. For our last example involving quadratic methods, let's take a look at a slightly different equation. We're going to find all alpha in the interval 0 degrees to 360 degrees. So if we're using our calculator, we'll need to make sure that we're in the degree setting that satisfy the equation sine alpha minus cosine alpha is equal to 1 over the square root of 2. Now, our success with solving equations hinges on the idea that we're using identical expressions. For example, I can solve 2x minus x equals 1 and get a single solution. But if I try to solve 2x minus y equals 1, rather than getting a single solution, I get an infinite set of ordered pairs that equal 1. So combinations of x and y. A similar thing happens when you try to solve equations that use two different trig functions. When you don't have common terms, it's hard to isolate your variable. So what are we going to do in a problem like this, where we have a sine and a cosine, and they're not the same? When we were working on identities in our Objective 5 and Objective 6 notes, we learned that one of the ways to transition from a sine to a cosine or a cosine to a sine is if you have a Pythagorean identity. Well, in a problem like this, we can force a Pythagorean identity by squaring both sides. If I square both sides, I'm going to introduce a Pythagorean identity that wasn't originally in the problem. So let's go ahead and try this strategy and see how far it gets us. Square here, square here. Be careful when you're squaring this binomial. You can't just distribute the squared. You actually need to distribute sine minus cosine times sine minus cosine. And then 1 over rad 2 squared is 1 over 2. Keep in mind, when you're squaring each side, you need to be careful that you're not introducing extraneous solutions. That may not be applicable in this example. However, we want to keep in mind that this is a possibility when I'm squaring. So over here, I get sine squared minus sine theta, sine alpha, cosine alpha, minus sine alpha cosine alpha plus cosine squared alpha equals 1/2. Now I can combine like terms and I can apply the Pythagorean identity. For the Pythagorean identity, I know that sine squared alpha plus cosine squared alpha is equal to 1. For combining like terms, I know minus sine alpha cosine alpha minus sine alpha cosine alpha can be minus 2 sine alpha cosine alpha, and it's still equal to 1/2. Getting closer to a solution, but we still need some identities because I started with a sine alpha and a cosine alpha, and I still have a sine alpha and a cosine alpha. And the same problem applies. We're not able to isolate the alpha until we're looking at something that's all in terms of a single trigonometric function. Thankfully for us, this is another identity. 2 sine alpha cosine alpha is equivalent to sine of the double angle. Now I'm down to a linear format trigonometric equation with a single trig function. I can solve this equation like I've solved previous examples. Subtract 1 to both sides. And at this point, I'm out of space on my whiteboard, so I'm going to erase and rewrite this equation towards the top of the board. I left off with negative sine 2 alpha is equal to 1/2 minus 1, or negative 1/2. Divide both sides or multiply both sides by negative 1. And then again, ask ourselves where on the unit circle from 0 to 360 is the sine of the angle equal to 1/2. This is going to give us 2 solutions. The first solution is in quadrant 1, so we write 2 alpha is equal to 30 degrees. And the second solution is in quadrant 2, so we can write 2 alpha is equal to 150 degrees. Solving each of these equations for alpha, we find that alpha is 15 degrees, and that alpha is 75 degrees. Now, I warned us at the beginning of the problem that when you're introducing your own squared function, you risk the chance of introducing extraneous solutions. So there's a possibility that one of these 2 answers don't actually satisfy the equation due to the square root relationship of having positives and negatives. In order to make sure we don't have an extraneous solution, we're going to need to plug both of these back into the original equation. So the original equation was sine alpha minus cosine alpha is equal to 1 over rad 2. If I plug in 15 degrees, I get sine of 15 degrees minus cosine of 15 degrees equals 1 over rad 2. Now I'm just trying to check my solution. I'm not trying to solve a new equation, and since 15 degrees isn't on my unit circle, I went ahead and typed it into my calculator. Sine of 15 degrees minus cosine of 15 degrees is negative 0.707. This solution on the right is not negative, so 15 degrees is extraneous. Let's double check 75 degrees. If 75 degrees is extraneous, we already found that these were the 2 possibilities. So if 75 is extraneous, it tells us that there is no solution to our original equation. Hopefully that's not the case. Sine of 75 degrees minus cosine of 75 degrees is equal to 1 over rad 2. Again, I'm going to type this into my calculator because I'm just trying to check my solution. An approximation is going to give me that clarification. I get 0.707106, etc. Let's compare that to 1 divided by radical 2. Are these decimal approximations the same? They are, which tells me that the solution to this equation is alpha equals 75 degrees. This concludes the video notes for Objective 7, Solving Equations with Inverse Trig. In class and during your assignments, you're going to be asked a variety of questions that rely on the foundations we've established here through the video notes. Just remember, as we've seen in this example, we need to make sure when we're solving trig equations that we are using a single trigonometric function. Everything is cosine, everything is tangent, or everything is sine. If that's not the case, we're going to need to use the identities that we've learned in the last objectives in order to make substitutions and keep all of our trig functions equal.